I'm going to start off again from the top, and if people watching hadn't guessed, this is the first MelMag live stream. I'm Will. This is the talk show where you get a chance to ask questions of the people who make our city and state what it is. If you're following live on Facebook and have a question for tonight's guest, just leave it in the comments below. On tonight's show, we're joined via video call by astrophysicist Associate Professor JJ Eldridge of the University of Auckland, New Zealand. JJ is a fellow of both the Royal Astronomical Society and the Astronomical Society of Australia, and on Thursday will be in Melbourne to talk binary stars and non-binary gender at a Midsumma Festival Science Lecture. JJ, for the second time, I do apologise. How are you doing?
I'm very well. I'm enjoying it.
That's good. That's a relief. At least at least that's going well. So a fairly fundamental question to start out with, because I figure that a lot of people watching might not know, because it's science, and science education is not at the highest rate that it could be. What are binary stars?
Binary stars are just stars like our sun or other stars, but they're not on their own. You know, I mean, our sun isn't really on its own because it's got the planets going around it. But we can imagine if we, say, took away the Earth and put a different star in its place, and so you have two stars orbiting around each other, that would be a binary star system. And normally they don't do anything too different until one of them gets older and bigger and the stars can get in each other's way, and things can happen that are very different to what you'd expect for a star like our sun that's a single star on its own to go through.
Why is it important to study stars like these? Or star systems like these?
Because it's really cool.
That's a good answer.
Well, no, so the reason to study stars anyway is that we're all made of star stuff. Okay, so like the carbon, the nitrogen, the oxygen, the iron in our bodies, which are key elements, come from different stars. Now, we can trace which element comes from which type of star. Now, we know that the carbon and the nitrogen come from stars like our sun when they get very old and die. I mean, not obviously our sun, but a previous generation of star. We know that oxygen comes from exploding massive stars, which are about 8 or 9 times the mass of our sun. If those and things that are heavier explode, they produce lots of oxygen. And it doesn't matter if they're single or if they're binaries. Most of the oxygen in the universe is produced by those exploding stars. But iron is the interesting one, because without binary stars, we wouldn't have any iron in the universe. If a star like our sun was in a binary star system, and eventually interacted with its other companion and become a white dwarf, and then the star it was orbiting around then also gets older and interacts back with that white dwarf, they can explode in these very specific type of stellar explosions we call a thermonuclear supernova. And you get a sun's worth mass of iron in the universe out of these explosions. But we know they only happen in binary star systems. So, why is iron important, JJ? Because your blood has hemoglobin in it, which is the main element in that is iron, and that's why it's red, and that's how we can carry oxygen around our bodies to live. And so it's really important. And there's some other elements like gold, silver, and platinum that come from other types of binaries. So it's like there's really unique things that these things do that a single star just can't.
Are binary stars a common thing in the universe?
Yeah, so there's this. I'm trying to track this down because I'm trying to write an article, and somebody said, I can't remember who it said it for the first time, which is what I want to find out, that 3 in every 2 stars is binary, right? Which makes you hang on. So when you look at many stars in the night sky, some of those are binaries. Most of them are binaries. There's the Big Dipper, which has one of those stars. If you can look at it through a telescope, you see it's a double star system. But then if you look at those 2 stars that you see through the telescope and you look at their spectra, you realize they're also both double stars. So you've got this quadruple system. Stars like being together. And if you actually do a number count, something like 50% of the stars in our galaxy are in binaries, 25% are single, and the other 25% are in triples, quadruples, quintuples, and it can actually get quite complex. I think there is 1 or 2 known systems which have 6 or 7 stars known orbiting around each other.
Is that stable?
Well, that's the thing. They're stable now, but things may become unstable. And of course, stars change. I mean, it doesn't look like the sun's changing very much. It's growing about an inch a year, or in new money, that's 2.5 centimeters a year. But over billions of years, stars can get very big. And so that's where most in these multiple star systems, instabilities or problems happen when the stars get old and get bigger, so they're more likely to bump into each other.
So what does your research involve? Are you looking at images from satellites and from telescopes and sifting through the data, or is it something else? Is it something different to that?
Yeah, it's sitting in front of a computer. There's a really good cartoon I like from PhD comics, which is just like, it's one of the main characters typing away, suddenly gets really excited because they found a bug in their code. I'm a theoretical astronomer. And like maybe 30, 40 years ago, that would mean I would be thinking very hard about maths and trying to solve equations with pen and paper. But when I started my PhD about 20 years ago now, or 19 years to be exact, we were in the age where computers were just starting to get powerful enough to really solve problems, but in a new way. Whereas we'd use like one big computer to maybe make one model of a star. It was coming through in my time in my PhD and over the last few decades where we've got almost too much computing power. We can just find a problem and throw computing power at it. And so I make lots of stellar models. But then the other thing I've been working with colleagues around the world is, how do I compare my computer model to a star, right? I can't look at my model in a telescope inside the computer. I would just see the chips. And trying to take your models as far as you can as if you was observing them with a telescope, because then you can just take the light straight from a telescope and compare the two, and they kind of match, which is actually also quite cool, but it's an entire new branch of physics of how you try and combine those things together.
It's it's very different to, I guess, the public perception of the gazing into the telescope at the night skies and seeing the seeing the universe around in the way that I guess that people traditionally see it, which is through the really really cool pictures you get from the Hubble and from, but even just some particularly good backyard astronomers with
those images from Hubble are science images, right? And
they're
so
false color and everything, aren't they?
Yeah. So they're not just pretty. I mean, they are pretty pictures, but there's actually data in there. One of the most well-known ones is something called the Hubble Deep Field, where they just stared at a patch of sky for a week, or is it a couple of weeks, just to try and see all the faint galaxies. And every pixel in that image that's got some photons or light in it detected is a galaxy. And so that sounds silly, just counting galaxies, but from the colors you can work out maybe how far away they are. And so even though this is a wonderful image of what is otherwise a blank piece of sky, if we didn't have the Hubble Space Telescope, you can still do science with that.
I think the first time that one of those images was created, it was. I'm just going to hold you there. I think my mic might be doing something weird. We'll see. There we go. I think I'm back. I think the first time the Hubble produced one of those images was it was pointed at a blank point in the sky, and it wasn't known what to expect at all, wasn't it?
Yeah. No, I mean, and that's one of the amazing things that's happened over my time as an astrophysicist, is we are now peering ever further and deeper back in time, which is kind of exciting. We're starting to see the universe just as it started to become transparent, which is kind of interesting. But you're right, because of all these computer images, even observers now who do the observation aren't looking for a telescope. They're using those computer images because our eyes are just not sensitive enough. We have to use these CCD cameras, and we want to see all the wavelengths of light, not just that our eyes do. But there is something very cool about sometimes going to a telescope, especially if you go to one of the. I haven't done this, but I know colleagues who have gone to these observatories which are at 2 or 3 kilometers altitude, and you can just see the night sky is wonderful out there because you're so high. You have trouble breathing because it's very rare atmosphere. But yeah, it is kind of cool. If you're an observer, you get to go to lots of fun places to observe the night sky, even though your real data is locked in a computer, which you can look at anywhere, mostly on laptops nowadays.
Not quite the glamour job it used to be, hey?
Well, there is the telescope called Sophia, which is, I don't know about glamorous, but it's one of the most extreme telescopes there is. It's a 747 jet, which has a telescope in the back of it. And
wow.
this is the observing time to get as an astronomer, because you get to go and fly on the flight, taking observations in real time from a telescope that's the same size as a Hubble, but you can just be in the next cabin away from where the telescope is, which is in the open air, pointing at the sky. And it's just you think are crazy having a telescope on an airplane, but it works. And the good thing is, it's not like Hubble. Don't have to get in a rocket to fix it. If anything breaks, you can fix it on the ground before you fly the next day.
I'm assuming the reasoning behind that is to get as clear a view of the sky as possible with as little atmosphere as possible.
Yeah, yeah, yeah. So it's an infrared telescope. So actually, it flies above the water layer. So it's the best infrared telescope that you can have that's Earth-based, even though it flies, so it's not technically an Earth, but you get the idea.
Well, I'm just conscious of time, so I will just move on to the other part of your lecture that will be coming up on Thursday. It's part of the Queers in Science lecture series, and the Queers in Science group exists to empower and include LGBTIQA plus people with involved in science. You are transgender and non-binary. Are scientific fields generally not inclusive for queers?
Yes and
in
no.
your experience, I mean.
It depends where you are. So I mean, I'm lucky that I got to my permanent tenured position in Auckland and then came out. And I think that gives me a lot of privilege and a lot of standing, because then it's like when people have seen me and I've been myself now at conferences, I can tell you one thing: being myself is so much better than trying to hide anything. I am so much more productive and confident and get so much more work done. I think that's the main benefit to me. Back though, when I was doing my PhD, I don't think I was in a very different place. I didn't have that privilege, and so I actually hid things much more. There's always been queer people in science. Actually, when you look at the history, I've started discovering that there are more queer people in the history of science than perhaps we actually think. And even some of the quite famous ones, there is good evidence that they were queer. But it's changing. And New Zealand and Australia, in my experience, are really kind of leading the way, as well as some universities in the States, in terms of making science in general more accessible to everyone, not just queer people, but people of colour and the entire diversity of humanity, because we want to get more ideas, because the only way we're going to solve these difficult problems is if everyone can come along. If we're all thinking the same thoughts and all look the same, there's no way we're going to solve those problems. I've gone off topic from your question, but the answer is I think things are changing, and if they hadn't changed, I would not be myself today talking to you.
I'm curious. My camera's doing that thing again. I'm gonna have to contact Elgato and complain quite a lot. There we go. I think we're back. So what I'm curious about is what is it that makes the Australian and Kiwi area science communities more? What is the difference that makes them better places or good places to work?
I don't know. I mean, I think I'm also in a very privileged position that when I moved to New Zealand in Auckland, there was a changeover to a new head of department, and I think there's a significant shift towards younger people, or the general age of the academia seems to be decreasing at the moment, or is less than it was in, say, Europe. I mean, where I did my PhD in the UK, there's a long history. Those universities are very, very old, right? And so there's a lot of ways that things are done, trying to change things. They are changing very slowly now, but maybe in Australia and New Zealand, it's the fact that there are more young academics that want to make changes, and also the institutions themselves, even though there's still institutions and there's still a lot of inertia to try and make changes, people are really waking up to the fact that we need to make these universities inclusive. There are conferences, I know, in Australasia on making your university inclusive and equitable for all your students, because actually if you have students paying money to come to your university, you want them to do well, because otherwise they're wasting their money. I mean, and nowhere's perfect, but especially in the physics department in Auckland, there is a really big group of us, and actually even in the wider faculty and even wider university, there's so many people I know that are trying to make the university more inclusive, especially for queer people. It makes a change, and it's given me the confidence. And then I know that just by being myself, by queering the academy in some way, just by being there, I know that means a big deal to students, all queer students, not just those who are trans or gender diverse.
It actually leads into my next question, which was, do you ever have young queers who are just starting to study astrophysics and other sciences ever coming up to you and either finding you as someone they can talk to about their experiences, or even just to, I guess, admire your achievements as a queer in the field?
Well, it's just seeing themselves in the institution. That can be enough. Yes, is the short answer to that. I have now got tissues in my office because of the number of people I have coming into my office at times just to talk to me, just for emergencies. But yeah, after my first lecture, I normally I can tell the people who are coming down to say thank you, because so after the first lecture of any course, the people just want to ask questions. And normally in my stage 2 or 3 physics courses, this never happens. But in my stage 1 course, where we teach stage 1 astronomy, which is the general education course for all people, people at the university. So, you're not teaching to scientists, you're teaching to everyone. In that class, just by being myself, there was always a handful of students that ask afterwards. And from statistics, that's going to be the case. If we have 300 students, there should be somewhere between about 10 to 30 queer students in that class. At least 10 trans people, just because of the numbers.
I am conscious of the fact we did have a bit of a late start there, so I'm going to wrap things up there. Thank you so much for your time, JJ, and for your really appreciate, and for putting up with the technical issues we had before. Have a good night, and just some details on. I will get to. I just need to make sure mics are correct. First stream issues. Here we go. Yeah, thank you, JJ, for taking the time to talk to MelMag. JJ will be presenting the lecture "Exploding Binaries, Stars and Gender" at the Royal Society of Victoria on Thursday night. General admission tickets are just $5.50 from rsv.org.au. You'll also find a link on the MelMag website, which is also having issues today, which is a great. It's a great day for this stream, isn't it? As my camera locks up again. That's all for today, thankfully. On Tuesday, the 14th of January, I'm Will Kurlich. See you again soon.